Scientists have created a solid material so light it can balance on a single blade of grass. Graphene Aerogel is a carbon structure that is barely denser than the air we breathe. The cylinder of graphene aerogel rests on top of a delicate flower's petals, causing zero bending or indentation. It is one of the lightest solid materials known to science. To understand how this material is constructed, we must look at its basic building block, graphene. Graphene is a single layer of carbon atoms arranged in a hexagonal honeycomb pattern. Graphene is a two-dimensional material. It has width and length but is only one atom thick, meaning it has virtually zero physical thickness while exposing a massive surface area. Imagine a sheet of atomic-scale chicken wire made entirely of carbon. It is incredibly strong, flexible, and conductible. To make the aerogel, scientists must turn this flat sheet into a 3D structure. Turning flat 12 sheets into a 3D structure is like building a microscopic house of cards. Engineers crumble, stack, and link the graphene sheets so they support each other in 3 dimensions. The synthesis starts with graphene oxide dispersed in water to form a gel called a hydrogel. To turn this hydrogel into a dry aerogel, the water must be completely removed. Normal drying fails. As water evaporates, surface tension creates capillary forces that pull the graphene sheets inward, crushing the delicate carbon framework into a collapsed, useless pile. Think of a wet sponge made of fragile spun sugar. Drying it in the sun forces the escaping water to pull the sugar fibers together, shriveling the sponge into a hard, tiny, collapsed lump. To prevent collapse, scientists use freeze drying. First, they flash freeze the hydrogel, turning the water into ice. This locks the delicate carbon skeleton rigidly in place. Next, they lower the air pressure. This forces the ice to turn directly into gas, skipping the liquid phase entirely. In a process called sublimation, the water leaves without exerting capillary forces. This is like drying the frozen sugar sponge in a vacuum. The ice turns to vapor without melting, leaving the sugar structure completely dry but retaining 100% of its original puffed-out shape. However, raw carbon sheets are held together only by weak physical forces. Without chemical bonds to hold them, the sheets slide past each other, making the aerogel brittle and fragile. To solve this, scientists introduce chemical cross-linkers, such as polymers or carbon nanotubes. These additives form strong chemical bonds that act as weld joints connecting the graphene sheets. It is like building a house of cards and putting a drop of super glue on every joint. The cards can no longer slide, turning a fragile stack into a single, solid, and resilient frame. This cross-linked network locks the carbon sheets in place. When you squeeze the aerogel, the joints distribute the force throughout the entire structure, preventing localized structural collapse. The resulting material is incredibly light. Graphene aerogel has a density of just 1.6 mg per cubic centimeter, making it one of the lowest density solids in existence. To put that in perspective, dry air has a density of about 1.2 mg per cubic centimeter. The solid carbon skeleton of the aerogel is barely heavier than the air itself. This is because 99.8% of the aerogel's volume is empty space. The solid carbon struts occupy only 0.2% of the space, with the rest filled by air. Imagine building a massive mansion out of hollow, paper-thin plastic straws. The mansion occupies a huge volume, but because it is mostly empty air, it weighs almost nothing. That is the aerogel. Despite being mostly air, graphene aerogel is highly elastic. You can compress it to over 90% of its original volume, and it will spring back to its exact shape without damage. The aerogel can endure thousands of heavy compression cycles without losing its bounce. The microscopic carbon walls bend but do not break, preventing material fatigue. It behaves like atomic memory foam. Squeezing it stores mechanical energy in the bent graphene sheets, and releasing it allows the cross-linked joints to push the structure back to its original shape. Graphene aerogels are also thermally resilient. They remain stable in extreme cold down to liquid helium temperatures and handle high heat, making them excellent thermal insulators for space exploration. The chemical surface is hydrophobic, meaning it repels water, and lipolytic, meaning it strongly attracts oil. Water beats up and rolls off the surface, while oil is instantly absorbed into the pores. This selectivity allows the aerogel to absorb organic solvents and oils up to 900 times its own weight in a matter of seconds, acting as a high-capacity sponge for toxic spills. Normal kitchen sponges are non-selective. They absorb both water and oil. If you toss one into an oil spill, it fills up with seawater, leaving the oil floating on the surface. Graphene Aerogel floats on the water and drinks up only the oil, ignoring the seawater. It leaves the ocean clean, separating oil from water with near-perfect efficiency. Once full, the aerogel is brought out like a normal sponge to collect the clean oil. Thanks to its elastic recovery, it springs back to its clean state, ready to be reused immediately. Historically, the main barrier was cost. Manufacturing the graphene oxide raw material was difficult and expensive, costing over $450 per gram, which restricted aerogels to lab experiments. However, new manufacturing breakthroughs have driven synthesis costs down toward $10 per gram, making large-scale commercial production viable for the first time. With lower costs, we can deploy large graphene aerogel booms in the ocean to clean up industrial spills, offering a highly cost-effective and environmentally friendly solution. Beyond cleanup, the aerogel's high electrical conductivity and massive surface area make it ideal for next-generation energy storage, powering fast-charging supercapacitors and batteries. Graphene aerogels are unlocking new frontiers, from high-performance insulation and planetary space probes to flexible sensors and green hydrogen catalyst supports. By turning flat carbon sheets into a three-dimensional marvel, materials science is reshaping the future. Thank you for watching Layman's Field. We hope to keep bringing knowledge for everyone.